is it possible to start with something that's, in a sense, finite, whittle it down, and end up with something that is irreducibly infinite? Okay, let's start with an algebraic field. Remember, an algebraic field is just a set of numbers where you can take any two of those numbers and combine them using the rules of algebra. Addition, subtraction, division, and what you end up with is still an element of that field. So it's a set of numbers that coalesces in a certain sense. Take some numbers out of that algebraic field and use them as coefficients to make polynomials. And use those polynomials to make a ring by allowing the polynomials to combine using the operations of addition and multiplication. What you have now is a finitely generated ring of polynomials. Now, a ring is somewhat like an algebraic field, but it's less restrictive. It's just the operations of addition and multiplication which are guaranteed, when applied to any two members of your ring, to produce another member of the ring. So, for example, the integers form a ring, but they don't form an algebraic field. Okay, so we've got this ring of polynomials, and it's finitely generated because we started with some finite subset of polynomials and used them to form the whole ring by combining them using addition and multiplication. Here's the question. Okay, what happens if we then want to whittle down that ring even further by saying, well, I'm going to apply some transformation. Let's say it's the transformation that takes x to minus x. And I want to find only those things in my ring of polynomials that are invariant under that transformation, that don't change. For example, x squared doesn't change under the transformation x to minus x, but x cubed does. Okay, so we started with our finitely generated ring, we've whittled it down. Do we still have a finitely generated ring? Is this ring of invariance finitely generated? Well, you might think it has to be. We started with something that's finitely generated, we took a subset of that, it's got to be finitely generated still. And for many people, for many years, people thought that was the case. And this was the subject of Hilbert's 14th problem. He wanted to prove that whatever polynomials you started with, whatever algebraic field, whatever transformation you applied, you had to end up with a finitely generated ring of invariance at the end. But in 1959, Masayoshi Nagata proved that this was not the case. And he did it by carefully curating a counterexample to show that in a certain sense, you can squeeze the infinite out of the finite.